Hello everyone, my name is Aliyah Postell. I am a junior at the University of Arizona, and this past summer I did a research project with my mentor Jay Gallagher about the NGC-1275 high velocity system and the Verging merge that will come from it. And I also had help from Dr. Ralph Catula, who ran the RU at the University of Wisconsin-Madison. And yeah, with that, let's get into it. Okay. So I phrase this in a story. So first we started with our setting. We had a galaxy located within the Perseus cluster who was rapidly approaching an explosive fate. And our plot involves many calculations, code updates, and a lot of project adjustments later. And we reached a climax of finding that the galaxy fit the suspected criteria of a jellyfish system with some interesting anomalies. And our conclusion is, the general question of where do we go next? So first we wanted to set the scene, the where. For this phenomenon to occur, we need for nature to provide an ideal environment. So the environment of the Perseus cluster is dense and bounded. Imagine a rubber band ball that's crushing in on itself. It's fast. Like fireflies on a windy day, the galaxies are moving rapidly, spinning around and around. It's very, very hot. Lots of hot gas produces the ram pressure stripping process, which I'll explain later. So, like I said, imagine a rubber band ball, lots of fireflies floating around it, and it's on fire. But our high velocity system says, that's good for me. I like that. Let's dive right into it. Disclaimer, this is not accurate. So then we move on to our plot, what we've been plotting, literally the how. See what I did there. So here we have a picture of our high velocity system where I'll outline some few things. So let me use my little laser pointer. So down here, the super bright spot is NGC-1275. We can see it has arms around here and around here. And up here is where we have our high velocity system, which is, we believe to be a spiral galaxy with some anomalies that make it an interesting kind of system, where we propose that these are what would be its arms. And here we have our infalling velocity, where our high velocity system is moving, and because of, astronomy's weird compass system, it's moving about southeast down towards the center of the Perseus cluster, also known as NGC-1275, and pushing back at it is the ram pressure, which leads to the ram pressure stripping process. So what exactly is that? So here I have a video of an artist's impression of the ram pressure stripping process. Just play. There you go. So here we have a galaxy moving. This is, imagine its infalling velocity being upward, and we have our ram pressure pushing downward we have these dust filaments streaming off of our spiral galaxy. So that's what we spent the summer observing, the dust filaments and the properties of them. So now we move on to when will this happen? When will this, like the time scale of the high velocity system approaching the center of the Perseus cluster? Approximately 30 to 40 million years. That seems like a lot, but for a time scale, the sun's galactic year, the total time to orbit around the Milky Way, is about 200 million years. So this is actually, in the grand scheme of the universe, happening relatively soon. So some basic goals for our project were to identify the main regions of interest, which are jellyfish filaments, and which are normal galactic materials. Our second goal was to measure. We wanted to measure the clouds, the mass, the optical depth, transmission, all those great things. And then we wanted to analyze. We wanted to analyze the mass and its properties, then compare our findings with molecular clouds within our Milky Way. So some measurements we made. We wanted to find area, flux, transmission, optical depth, distance, and mass. And because I'm a math major, I wanted to do everything by hand. But when you're dealing with something as massive and complex as galaxies, nevertheless galaxy systems, you can't do everything by hand. So we had to use some code, which I had help with by Dr. Ralph Katula, to take a number of regions and calculate out these numbers, which here's an older picture I had from DS9 where I'd messed around with the filters, and all of these dark regions you see here are what we wanted to study, these dust clouds, these dust filaments. So yeah, so here will be our findings, the what. Here's what we found after all the nitty-gritty calculations, all the code changes, number crunching, all that good stuff. So some plots I made using TopCat mapped out the area versus mass over 3 different filters for the galaxy. So we had 435, 550, and 625. And what we found was that this was reliable data. We see that the larger the larger the area, the larger the mass. So bigger clouds had greater mass within them. So check mark there. And then I did some plots about the histograms of mass over the different filters. So the frequency of how many of these clouds we can find, how many of these massive clouds. And we found that the levels of mass were typical with clouds in a galaxy. So another check. And we compared these findings with other papers out there studying jellyfish systems. And here's a model from one of these papers. And what we found is our high velocity system, which I flipped here on the side, most closely resembles this middle frame here, where we can see we have our supposed center of the galaxy, and we have dust filaments coming off of what seems like one side of the galaxy, and imagine it in the perspective of the universe, where these darker regions indicate larger mass, and the more sparse dots indicate smaller mass clouds. But when I mapped out that using TopCat, I wanted to test for a correlation with distance. So the distance from the center of the galaxy and the inferred mass. And I wanted to see that as things were closer to the center, if they were larger, and farther out, if they were smaller. And I didn't see that correlation. In simpler terms, the stuff further away was not massive, was less massive. It wasn't happening here. So we want to know why, and that's kind of an ongoing question we have going forward. So one famous astronomer that had conducted research on the high velocity system of NGC 1275 was Vera Rubin. And when posed with the question, how would you define this shadow spiral, this high velocity system, she said, "We believe that the observations can most simply be interpreted as an almost edge-on, late-type rotating system superimposed on NGC 1275. Very fancy, very cool, she's amazing. But it almost it basically confirms in a more scientific sounding way of what we found. We found that the galaxy itself is tilted. We're viewing it from the edge rather than face on, and late type because the impact is rapidly approaching the 30 to 40 million years. And it's a rotating system because we can see that the dust filaments are more on one side of our high velocity system. So our high velocity system is doomed for impact. The high velocity system is infalling approximately 8 times faster than the Milky Way and Andromeda plane collision. Like I said, the time scale, it's a lot faster compared to the movings of our side of the universe. and the impact will produce supersonic waves across the galaxy and the Perseus cluster. So it'll be a spectacle, to say the least. So why do we care? What's next? What do we do now? So some future plans we had, Jay and I, some questions we had were, how do these regions compare with those in other jellyfish systems? How do these molecular clouds compare with those in our Milky Way? And how can we use the region masses to calculate ages of the clouds and star forming regions within the clouds and relate that to the age itself of the galaxy? We had a lot of plans for the summer that 2 months is not nearly enough time to do all that we set out to do. So we have plans going forward. And another quote from Vera, although the morphology of the intervening galaxy is somewhat unusual, any alternative model seems so contrived as to be practically unacceptable, which is her way of saying she is rather confident in her findings. And I believe her. The research we conducted is nearly spot on with what she did, but she did it a whole lot cooler because she's Vera Rubin. And with that concludes my presentation. I will gladly take any questions. Thank you.
Nice talk, Leah. I wanted to ask about the infall time you mentioned, which I think you said was 30 to 40 million years.
Yeah.
Is that also, was that based on a comparison with the simulation that you mentioned? That is, it's going to take that long, the simulation predicts it, or is that an observational estimate?
That was more or less an observational estimate based on some other research that a mentor, Jay Gallagher and Ralph Catula, had done together. They measured the velocity of the dust filaments and the velocity of the galaxy itself, and kind of just cranking out some numbers and everything with like the velocities of the filaments and like the general scale of things. That was a number they had come up with. So that was kind of basing things off of some past research done and combining it with what I found over this past summer.
Great, thanks.
What exactly is a jellyfish galaxy? I have to know.
So jellyfish galaxy, which was coined because it looks like a jellyfish in a way. I have kind of like this picture right here. So we have our main center of the galaxy, and what makes it a jellyfish is it has these streams of dust filaments. The ram pressure pushes against the galaxy and leads to the stripping process that leads to these cool little filaments, which is what we spent most of the summer conducting research on. This is like the most well-known jellyfish galaxy out of like the universe, or at least to me. I didn't know what any of this was before starting the program, but I learned a whole lot over those 2 months. So yeah, these filaments were our main area of research over the summer.
Gotcha. And then my other question was, how far away is the one that you were studying?
Whatever the distance is from here, from us to the Perseus cluster, which I'm so sorry, I can't remember off the top of my head.
No worries. Well, thank you so much, Aliyah.